For decades, automotive safety was a strictly physical equation: brakes failing, steering column snapping, steel bending. But today, a vehicle can do the unthinkable. It can cause a catastrophic accident even when its hardware is working flawlessly. Autonomous systems face what engineers call the open world problem. The real world isn't a closed testing track. It is a chaotic environment filled with an infinite number of unpredictable variables that no programmer could possibly write code for in advance. Modern hazards often stem from a failure of perception. Even when cameras and radar capture the road perfectly, the algorithm behind them can encounter a combination of shadows and motion it simply has no frame of reference for. True safety in the autonomous era requires an entirely different approach. It demands mapping the extreme limits of machine comprehension itself. This chart shows how the international safety standard, known as SOTIF, visualizes those limits. It divides all possible driving scenarios into a cartographer's map of 4 distinct territories, sorted by what we know and what is safe. The first 2 territories are Area 1, the known safe, and Area 2, the known unsafe. These are the illuminated regions. Engineers have mapped these scenarios, anticipated the hazards, and prepared the system to handle them. But then there is Area 3, the unknown unsafe. This is the blank space on the map. It holds unpredicted, dangerous scenarios that the system has never seen and doesn't know how to survive. SOTIF provides the framework for mounting active expeditions into this void. Engineers hunt for these invisible dangers and drag them across the border into the light of the known world so they can be addressed through better design. The safety of a self-driving car is tied to this process of identification. By shrinking these dark spaces before a vehicle reaches the consumer, manufacturers reduce the probability of the system being surprised by a reality it cannot handle. So how do you find something you don't even know you're looking for? The first method is the brute force of massive scale. Manufacturers deploy fleets of test vehicles, letting them roam public roads for millions of cumulative miles. This is a deliberate mathematical strategy to increase the probability of encountering rare 1-in-a-million events. They are lying in wait for the perfect storm, a sudden blizzard obscuring a sign, odd debris falling from a truck, or decaying lane markers tricking sensors. Because human imagination cannot list every chaotic variable on Earth, engineers rely on staggering amounts of time and distance to force reality to expose its hidden anomalies. The second method of exploration takes an active approach, intentionally hunting for the machine's breaking point by forcing it into difficult environments. This chart visualizes what engineers call a corner case. A corner case occurs when 2 normal, everyday events overlap in a way that suddenly confuses the system logic. Test drivers actually engineer these exact moments. They might combine the intense glare of a setting sun with a lead vehicle slamming on its brakes, recording exactly where the sensor fusion algorithm reaches its performance limit. Stress testing these parameters in difficult combinations exposes blind spots. It allows developers to address logic flaws before they trigger a real-world collision. But the environment isn't the only source of chaos. The most unpredictable variable on the map is actually the human sitting inside the car. SOTIF requires testing for the naive user. Everyday drivers will inevitably misunderstand the technology. Using highway features on dirt roads, taking their eyes off the road, or ignoring alarms to take control. An autonomous system is incomplete if its safety model only accounts for physics and logic. It has to survive the irrationality of human nature. Exploring reality mile by mile is slow and expensive, which leads to an obvious question. Why don't engineers just map these unknowns instantly by running millions of virtual computer simulations? The SOTF standard warns against relying entirely on virtual tests. Simulations, while efficient, are ultimately incomplete models. They lack the messy, infinite detail of physical reality. Code cannot perfectly replicate the random electrical noise of a physical radar sensor, the contradictory social cues of pedestrians at a crosswalk, or the exact friction of a rain-soaked road. Virtual exploration is a tool for finding baseline flaws. But safety validation must always be anchored by forcing the system to face the unforgiving imperfections of the real world. At the end of this massive undertaking, it feels like there should be a finish line. The engineering team illuminates the dark areas, patches the vulnerabilities, and finally certifies the vehicle as safe. But there is a final reality to SOTIF. The moment a software update is pushed to the car, or the algorithm's decision-making logic is tweaked, that map of risk resets. Expanding the car's top speed, changing its lane change policy, or upgrading its sensors creates new, unmapped hazards that did not exist yesterday. Autonomous safety is not a permanent certificate. It is an evolutionary journey across a reality that never stops shifting.